And so I want to take some incredible liberties in computer science. You know, if Dave Patterson and John Hennessy, and I know that Pat Hanrahan is sitting here watching me, you guys are going to go nuts. If you guys, this is called CEO math. This is not computer architect math. This is called CEO math. But it illustrates the point exactly. So let me first show you why CUDA makes a lot of sense. This is an illustration of co-processing. Now, I realize there's a lot of words. I'm just going to, if you can bear with me, there's some simple math we're going to do. There'll be a short test at the end of this presentation. So this is simple math. The first section on top is an example of a program that is parallel intensive. And on the bottom is an example of a program that is mostly sequential. And the way that I simply made it is the serial code part of the parallel intensive program takes about 1 second to run. Whereas the parallelizable part of the code takes 199 seconds to run, which makes sense. It's an enormous amount of data. It takes one CPU core and a very long time to run. So 199 seconds. In the case of the sequential program, the serial component is about 150 seconds, and the parallel component is 50 seconds. This represents one CPU core. Now, of course, the way to make this program run faster, make these programs run faster, is simply to make the CPU run faster. And so year in and year out, we would add more transistors, and the way that we would use those transistors is we would enhance or increase the amount of speculative execution that we do. And we're searching desperately for instruction level parallelism. Meanwhile, we're pumping up the frequency, we're adding more cache, because the CPU is not particularly latency tolerant. And so we're adding all of those capabilities to the CPU year in and year out. And as a result, the CPU gets faster and faster, and over the course of the last 10, 15, 20 years, Moore's Law has translated to quite dramatic speedups. Well, at this point, it is relatively well known to all of you in the audience now that it's very, very difficult to find additional instruction level parallelism. And pushing that CPU to go faster, that incremental amount of frequency translates to a disproportional amount of power. And we're trying to fit CPUs into a finite server room, and so you have a finite amount of power that you can really consume. And so we realize now that a single CPU core making it faster and faster all the time is not the best approach. And so why don't we make it parallel? And so I'm going to illustrate now. Suppose over time, I gain access to 10 times the number of transistors as my first column with one CPU core. And I'm going to use those 10 times of transistors in parallel cores, 500 parallel cores, where each of these little tiny parallel cores is equivalent to one very, very well-designed CPU core. Okay? So one CPU core equals 50, and I have 10 times more transistors, and so there's 500 parallel cores. Now, that little tiny parallel core has a deficiency. That little tiny parallel core is deficient in the way that when it runs serial code, because it doesn't benefit from all of the speculative execution technology that has been incorporated into today's modern, exquisitely designed CPUs, it runs serial code badly. It runs serial code badly. So let me make it 5 times more badly. And so that 1 second becomes 5. But for parallel code, it's very easy for the parallel processor to accelerate. And let's say that I simply accelerate that 500 times. And so if you simply do this math, what you'll discover is that the parallel application is, in fact, 40 times faster. However, for most applications, like the operating system, or whatever happens to be that's vastly serial, vastly sequential, in fact, it is much, much worse, 3.5 times worse. Now, Gene Amdahl observed this 4 years ago. It's called Amdahl's law. And whatever is the serial part of the serial component, sequential component of your program, will ultimately limit the benefits that parallel computing will bring to you. And this is a perfect illustration of that. Well, suppose I went the other way on it. Suppose I made this 10 CPU cores, what modern world calls multi-core. Those 10 CPU cores would still run the sequential part of the application just as fast as one. And so it was still 1 second. However, that 10 CPU cores, and I'm giving it the benefit of the doubt here, Most CPUs, most multi-cores, as you know, when you put too many CPUs on CPU cores on the same chip, it contends against the cache, so there's a bit of a cache CPU utilization back pressure. The caches become a lot smaller. You have to go off chip whenever there's a cache miss, and they all have to share that memory bandwidth. But let me ignore that just for a second. I mean, this is a CEO math after all. Let me just divide everything by 10. And so what you get as a benefit is approximately 10 times speed up. So 10 cores for parallel code gets 10 times speed up. For transcoding, for example, transcoding video or something that's easily parallelizable, you can see the 10 times speed up. In fact, what you'll also see is that for the serial code, 150 seconds translates to 150 seconds, and the 50 seconds translates to 5. You get 1.3x. In fact, of these three choices, the multi-core is the best answer. The multi-core is surely the best answer so far. It's the best answer because it speeds things up moderately, less good than parallel computing, but it did no harm. We can't create a product for you. We can't create an architecture for you. That is an advancement in some fundamental area, but an enormous step back for the vast majority of the applications. And so we looked at this and we said, you know, why do it this way? Why does it have to be A or B? Why can't the world be A and B? And so we created this architecture called heterogeneous computing. Instead of 500 parallel cores or 10 CPU cores, we use the same amount of area for one CPU core and 450 parallel cores. That one CPU core is still the most modern CPU core you can imagine. It's sitting right there, exquisitely designed, sitting in every single PC because it has to run Windows. And that 1 second still is 1 second. I said something funny. I didn't mean to. Okay, maybe I did. All right, so that 1 second became 1 second, and the 199 seconds became 0.4. It was sped up 450 times. So as you can see, we saw a speed up. What's amazing is we saw a speed up here for the parallel application of nearly 200 times. Between 100 to 200 times. An enormous speed up. And yet, on mostly sequential programs, it did no harm. It did no harm. And so, the most important thing in creating a new architecture is to make sure, number one, it does no harm. That everything that you used to run runs better. But for new applications, it has an enormous opportunity to take you to a new space. And now, over time, more and more people will realize this architecture exists, and they will adapt their applications to take advantage of all the resources inside your computer, eliminating more and more and more of the sequential dependencies inside your program. As a result, speedups will continue to enhance. That is the essence of heterogeneous computing. I apologize for all the professors in the world, in the room here, for taking such enormous liberties to demonstrate